Module 2, Lecture A, Tensors and Ops. By the end of this lecture, you will be able to create and manipulate TensorFlow tensors with specified shapes and D-types, apply common TensorFlow math and array operations to transform tensors, and explain TensorFlow broadcasting and shape inference in simple expressions. Creating tensors, constants, and variables. When working with tensors, it is important to distinguish between constant and variable tensors. Constant tensors keep the same values throughout computation, like fixed configuration data. Variable tensors also keep the same shape and type, but their values can change, which is essential when training neural networks and updating weights. Both kinds of tensors are fundamental to how models store and update information, but they play different roles in the computation process. When you create a constant tensor, you define its values, shape, and data type, so the computational framework clearly understands your intent. The values might represent fixed data, such as pixel intensities or geographic coordinates, and they do not change during computation. The shape describes the structure of the data, like a sequence or grid, and the data type specifies how the values are stored, such as integers or floating point numbers. Together, these choices create a stable reference that remains consistent throughout your calculations. Variable tensors are values in a model that can change during computation while keeping the same shape and data type. They start from an initial value, which might be a pattern, random numbers, or something based on prior knowledge. In tasks like modeling advertising spend versus sales or building recommendation systems, key parameters such as model weights, user preferences, and item characteristics are stored in these variables, so they can be updated as more data is processed. This allows the model to efficiently manage what stays fixed and what adapts during training. Python code, constants and variables. This script gives a basic introduction to TensorFlow constants and variables, with an emphasis on how tensor shapes and data types work. As you run each part of the script, you can see printed outputs that show how these tensors are defined and represented. By observing these results, you gain a clearer understanding of how TensorFlow handles different kinds of data. The goal is to help you become familiar with the fundamental building blocks used in TensorFlow programs. Before using TensorFlow, you may need to install it in your environment. The example command installs TensorFlow version 2.20.0 using a package manager. A quiet option is included to reduce extra installation messages. This installation step is essential if TensorFlow is not already available, because it provides the core tools needed to work with tensors and build machine learning models. We start by importing the operating system module so we can control environment variables, and we set the CUDA visible devices value to -1 to turn off GPU usage for TensorFlow, forcing it to run only on the CPU. This is useful when no GPU is available or when GPU acceleration is not needed. We then import TensorFlow and assign it the short name TF, which is a common convention that makes the code easier to read and manage when working with TensorFlow's many tools and features. This line displays the version of TensorFlow currently in use, allowing you to quickly confirm that the correct version is installed and active in your environment. Checking the version helps ensure that your setup matches the requirements of your project. It is especially important when other parts of the code depend on specific TensorFlow features or behaviors that may differ between versions. We begin by creating a scalar constant in TensorFlow with the value 3.5 and specifying that its data type is float32. This means the value is stored as a single precision floating point number. Using this format is common in machine learning because it offers a good balance between numerical precision and memory efficiency. In TensorFlow, you can create a one-dimensional constant tensor from a Python list containing the values 1, 2, and 3. By setting the data type to integer 32, each value is stored as a 32-bit integer. This kind of constant tensor is useful when you need fixed values that stay the same throughout the program's execution. We use TensorFlow to create a two-dimensional constant tensor, which is a small matrix with 2 rows and 2 columns. Each entry in this matrix is a floating point value of type float32. Because it is defined as a constant, its values do not change during execution. This makes it useful as fixed data that other operations in the script can use and build on. We use TensorFlow's NumPy method to print a scalar constant, so we can easily view its value as a standard NumPy array. We also check its shape to see its dimensions. Together, these steps let us quickly verify both the constant's value and its structure. In this example, we examine a vector constant by converting it from a TensorFlow tensor into a NumPy array so we can clearly see its values. We also print the shape of the tensor to reveal its dimensionality. Together, these steps quickly show both the contents and the structure of the vector constant. This line prints the matrix constant by first converting it into a NumPy array. Using the NumPy method presents the matrix values in a clear, readable format. This makes it easier to check the structure and contents of the matrix and confirm that it matches what you expect. In TensorFlow, constants cannot be changed once they are created. If you add 1 to a matrix that is defined as a constant, TensorFlow produces a new matrix instead of altering the original. This behavior shows that TensorFlow constants are immutable. It also lets you see the result of the operation while keeping the initial matrix unchanged. We display the original matrix by viewing its underlying NumPy array, which shows all its values in a clear, familiar layout. This makes it straightforward to inspect a matrix and understand its contents. It also helps us later compare the original matrix with any versions that have been modified. This line prints a new matrix created by adding 1 to every element of an existing matrix constant. The original constant is not changed. Instead, TensorFlow produces a separate tensor with the updated values. That new tensor is then converted to a NumPy array so it can be displayed. This illustrates that TensorFlow constants are immutable, and any change creates a new object rather than modifying the original. We use TensorFlow's variable function to create a tensor initialized as a 2x2 matrix of floating point values with data type float32. Unlike a constant, this variable can be changed after it is created. This ability to update its values makes it useful in situations where the tensor must be modified during computation, such as when training machine learning models. We begin by printing the initial values of the weight variable and its shape. To do this, we convert the TensorFlow variable to a NumPy array, so the values are easier to read. This lets us clearly see and verify the starting state of the variable before any updates are made during training or further processing. We create a small update tensor using TensorFlow's constant function, defined as a 2x2 matrix where every entry is 0.1. Its data type is set to 32-bit floating point. By matching both the shape and data type of the variable it will update, this tensor can be used smoothly in later operations without type or dimension mismatches. The code first checks that the shape of the variable weights matches the shape of the update step, so the dimensions are compatible. If they match, it updates the weights directly in memory. This is done using a TensorFlow method that adds the update step to the current weight values. Updating the weights in place like this is efficient and well-suited for adjusting model parameters during training. This line prints the updated values of the weights variable after it has been changed using an in-place addition. It first converts the TensorFlow variable into a NumPy array so the values are easier to read. By displaying these converted values, we can clearly see the effect of the update step and confirm that the variable was successfully modified. We define a bias variable using TensorFlow's variable creation function and initialize it with 2 zeros. Its data type is set to 32-bit floating point, so that all calculations involving this variable use the same numeric format. This consistency is important for reliable numerical computations, especially when the variable is updated or used in later mathematical operations. We update the bias variable using a safe assign operation that replaces its value. To do this, we add a constant tensor containing the values 0.2 and -0.1. This constant is defined with a float 32 data type, so it matches the bias variable. As a result, the first element of the bias increases by 0.2, and the second element decreases by 0.1, while keeping the data types consistent. The code prints the final value of the bias variable to verify that its update worked correctly. It converts the TensorFlow variable into a NumPy array so its current value is easy to inspect. This confirms that the changes to the variable have been applied and provides a clear result for verification. This script uses TensorFlow to show how constants and variables work with tensors. It begins by printing the TensorFlow version, then creates a scalar, a vector, and a matrix as constants, and prints their values and shapes to illustrate different tensor dimensions. It demonstrates that constants are immutable by creating a new matrix with modified values, while leaving the original unchanged. The script then introduces a variable tensor, updates it in place, and prints the new values to confirm that variables are mutable. Finally, it updates another variable while keeping data types consistent, highlighting how TensorFlow manages tensor operations and variable updates. Random and zero tensors. When creating tensors, you often initialize them with random values or with zeros. Random tensors are important for setting up neural network weights so that different units start with unique values and can learn different patterns. Zero tensors act as neutral starting points or placeholders, such as empty buffers or baseline images. In all cases, you control the tensor's shape and data type, so it fits your computation graph and works efficiently on your chosen hardware, whether that is a CPU, GPU, or specialized accelerator. When creating random tensors, you choose a probability distribution that matches your task, such as a Gaussian distribution for values clustered around 0, or an exponential distribution for positive skewed values. You also specify the tensor's shape, like a grid for a single image or a block for a batch of images, and select a data type, often a floating point format. The framework then generates random numbers that follow the chosen distribution and fit the requested shape and type, giving you a flexible way to simulate data, noise, and other conditions for model setup and experimentation. Zero tensors are useful when you need a reserved block of memory with no initial signal, ready to store future results or serve as a neutral starting point, such as an all-black image in computer vision. They work well for accumulating values over time or acting as placeholders for data that will be filled in later. It is important that the zero tensor has the same shape and data type as the tensors it will interact with, so operations like addition or stacking work correctly. Depending on the task, this might be a 3-dimensional zero tensor for video frames, a 2-dimensional one for a weight matrix, or a 1-dimensional one for a feature vector. But in all cases, you are controlling its structure from the start, so it fits smoothly into your computation. Python code random and zero tensors. This script uses TensorFlow to work with simple tensors, focusing on random tensors and tensors filled with zeros. It examines how these tensors are created and highlights their shapes and data types. The script also emphasizes deterministic randomness, meaning that random values can be reproduced consistently when needed. The commented line indicates installing TensorFlow version 2.20.0 to ensure the script uses a specific version for compatibility and reproducibility. Because the line is commented out, it shows that this installation step is optional. It may be assumed that TensorFlow is already installed, or that the user will handle the installation separately if needed. The code first sets an environment variable that disables GPU usage by making CUDA devices unavailable, which forces TensorFlow to run on the CPU. This is helpful for debugging or when no GPU resources are present. After that, TensorFlow is imported and given the short name TF, a common convention that makes its functions easier to use throughout the script. This code prints the version of TensorFlow currently in use. Knowing the exact version helps you check compatibility with other tools and libraries. It also tells you which features and improvements are available, since different versions can change or add functionality. In practice, confirming the TensorFlow version is an important first step when setting up or debugging a project. We set the global random seed to the value 42 using TensorFlow's random module so that any random numbers generated are the same every time the script runs. This makes the results reproducible, meaning repeated runs of the code will produce identical outcomes. Such consistency is especially helpful for debugging and testing because it allows us to reliably compare results across different runs. We use TensorFlow's random normal function to create a small random tensor with 2 rows and 3 columns. Its values come from a normal distribution centered at 0 with a standard deviation of 1, meaning they are spread around 0 in a typical bell-shaped pattern. The tensor uses the float32 data type, which is commonly chosen because it offers a good balance between numerical precision and memory usage. We use TensorFlow to create a small random tensor with 2 rows and 3 columns. Its values come from a uniform distribution, so each number is equally likely to be between 0 and 1. We also set the data type to 32-bit floating point, so the numbers are stored with that level of precision. We create a tensor that is completely filled with zeros, with a shape of 2 by 3, meaning it has 2 rows and 3 columns. The elements of this tensor use a 32-bit floating point data type. This kind of zero-initialized tensor is useful when you need a specific size as a starting point, such as a placeholder, or when you need a neutral value for later operations. We create a zero tensor that has the same shape as an existing tensor called random normal. To do this, we use the TensorFlow function that makes a tensor of zeros matching another tensor's shape and data type. This ensures the new tensor lines up perfectly with the original one. Such a zero tensor is useful when you need values of 0 that are structurally compatible with another tensor for further operations. We check the shape and data type of each tensor to confirm they are built correctly. First, we inspect the tensor created with a normal distribution, then the one created with a uniform distribution, verifying their dimensions and data types. We repeat this process for the tensor filled with zeros, and for the tensor that copies the shape of another tensor. These checks are important for debugging and for making sure all tensors match our expectations before we use them. The code first checks whether the random normal tensor and the tensor of zeros have the same shape, ensuring they can be safely added without errors. If their shapes match, it adds them together and stores the result in a new tensor called the added tensor. If the shapes do not match, it does not attempt the addition, and instead sets the added tensor to a special value that indicates the operation cannot be performed safely. We first display the values of a tensor, created with TensorFlow's random normal function, which produces numbers drawn from a normal distribution. To make the output easier to read, we convert this tensor to a NumPy array before printing it. We then do the same for a second tensor that has the same shape as the random tensor, but is filled with zeros. Converting this zeros-like tensor to a NumPy array and printing it lets us visually confirm the structure and contents of both tensors. To verify that adding zeros to a tensor does not change its values, we compare the original tensor with the tensor produced after adding zeros. We use a TensorFlow function that checks whether all corresponding elements in the two tensors are equal. Another function performs this element-wise comparison, and then we convert the result to a NumPy array so it can be printed. If all entries are true, it confirms that the addition of zeros preserved the original tensor values. This script shows how to create and work with tensors in TensorFlow. It first sets a global random seed so the same random values are produced each time. It then creates two random 2x3 tensors, one with a normal distribution and one with a uniform distribution, along with two zero tensors of the same size. The script checks and prints their shapes and data types, confirming they are all 2x3 float 32 tensors. Because the normal tensor and its zero counterpart share the same shape, they can be added, and the result is identical to the original normal tensor. A final comparison confirms that adding a zero tensor does not change the values of the original tensor. From NumPy to tensors. In numerical computing, you often begin with array libraries that handle multidimensional data such as images or time series. When you move to deep learning, these arrays are converted into tensors, which are the data structures used by deep learning frameworks. The underlying data does not change, but its format is adapted so the framework can process it efficiently, especially on hardware like GPUs. This conversion lets the framework optimize and run machine learning tasks effectively while taking advantage of its broader ecosystem. When you convert an array into a tensor, you are deciding not only to keep its values and shape, but also how it will be represented and processed. The tensor preserves the original structure, whether it is a simple list or a complex batch of images. You must also choose an appropriate data type, such as switching from integers to floating point values when you need more precision. Making careful choices about structure and data type helps prevent misinterpretation, avoids wasting memory, and supports efficient, accurate handling of large datasets. In many real workflows, data begins as arrays that are not yet suitable for modeling, so converting them into tensors is an essential step. Whether the data comes from climate measurements, social surveys, or robotics, transforming arrays into tensors with the right shapes and data types connects raw data to machine learning models. This conversion preserves the original structure while enabling integration into computational graphs, automatic differentiation, and performance optimizations. As a result, you can keep using familiar pre-processing tools while taking full advantage of tensor-based computation for learning and inference. Python code from NumPy to tensors. This script demonstrates how to convert NumPy arrays into TensorFlow tensors, with a focus on understanding their shapes and data types. As you run each section, pay attention to the printed outputs that show how the tensor dimensions and types are represented. The goal is to help you see how data moves from NumPy into TensorFlow and how its structure and type information are preserved during conversion. At the start of the script, there are comments reminding you that it depends on the TensorFlow and NumPy libraries. These notes explain that if these libraries are not already installed in your environment, you should add them using the standard Python package installer. Including such comments is a common way to make sure anyone running the code knows which dependencies are required. This helps prevent errors and ensures the script can run correctly. The code starts by importing 3 standard libraries called OS, Sys, and Math. These provide tools for working with the operating system, handling system-specific settings, and performing mathematical calculations. Bringing them in at the beginning prepares the script to use these capabilities whenever they are needed. This is a common way to set up the environment before the main logic of the program runs. The script tries to import the numerical library using a short alias, and if that library is not installed, it catches the resulting import error. When this happens, it immediately stops the program by raising a system exit with a clear message that the library is required. This behavior ensures the script does not continue running without its essential dependency, which helps avoid further errors later in the execution. The code tries to import TensorFlow using a short alias, and if TensorFlow is not installed, it catches the resulting import error. Instead of failing silently or continuing in an invalid state, it immediately stops the program. It does this by raising a system exit with a clear message that TensorFlow is required. This makes sure the user quickly understands that a missing dependency is preventing the script from running and knows they must install TensorFlow to proceed. This code displays the version of TensorFlow that is currently in use. Knowing the exact version helps you check compatibility with your project. It also tells you which features and syntax are available, since different TensorFlow versions can behave differently. We begin by creating a small 2x2 NumPy array containing the values 1, 2, 3, and 4, stored as 32-bit floating point numbers. Choosing this specific data type ensures the values use single precision. This setup prepares the array for conversion into a TensorFlow tensor, so we can observe how its data type and shape are preserved during that conversion. We begin by checking the shape of the NumPy array to see its dimensions, which tells us how the data is organized. This helps us understand the structure we are working with. We then look at the data type of the array to confirm what kind of values it stores. Verifying both the shape and data type ensures the array matches our expectations before we perform further operations. We can convert a NumPy array into a TensorFlow tensor using TensorFlow's convert-to-tensor function, which takes the NumPy array as its input. This conversion keeps the original data structure and values, but places them in a form that TensorFlow can work with directly. Once converted, we can apply TensorFlow operations and use the data in machine learning tasks more efficiently. After converting the NumPy array into a TensorFlow tensor, the code checks the result by printing the tensor's shape and data type. The shape shows the dimensions of the data, and the data type shows what kind of values it contains. Together, these checks confirm that the conversion kept the original array's structure and type intact. In this step, a NumPy array is converted into a TensorFlow tensor while explicitly setting the data type to float 64. This means the tensor will use double precision floating point numbers, which can be important for calculations that need higher numerical accuracy. By choosing the data type directly, you control how the data is stored and processed, which can influence both the performance and the precision of your computations. This code shows what happens when a NumPy array is converted into a TensorFlow tensor. It prints the tensor's shape, which stays the same as the original array. It also prints the tensor's data type, which has been explicitly set to float 64 during conversion. This illustrates that you can change the data type while keeping the original shape of the data unchanged. We begin with a NumPy array that has 2 rows and 3 columns containing the integers from 0 to 5 and using a 32-bit integer data type. This setup is used to show how such an integer array can be converted into a TensorFlow tensor. The key point is that the values remain integers during this conversion, so the integer nature of the data is preserved in TensorFlow. We convert an integer NumPy array into a TensorFlow tensor by using TensorFlow's convert to tensor function and specifying the data type as 32-bit integer. This step makes sure the new tensor keeps the same integer type as the original NumPy array. As a result, the data type remains consistent when moving data from NumPy into TensorFlow. This code displays the shape and data type of an integer tensor. The shape describes the tensor's dimensions, and the data type indicates what kind of values it stores. Together, these details give a quick overview of the tensor's structure and content. This is useful for checking that converting from a NumPy array to a tensor kept the expected dimensions and data type. We first compare the shape of the TensorFlow tensor with the shape of the original NumPy array to confirm that the conversion preserved the data structure. Matching shapes indicate that the data was transferred correctly. If the shapes differ, we raise a value error to signal that something went wrong. This check is essential for maintaining data integrity when moving from NumPy to TensorFlow. We first look at the first row of the NumPy array to get a quick view of the original data. Then we display the first row of the TensorFlow tensor, converting it back to a NumPy array using the tensor's built-in method, so it is easy to compare. By checking that these two rows match, we confirm that the conversion from the NumPy array to the TensorFlow tensor preserved the data accurately. This script shows how to convert NumPy arrays into TensorFlow tensors while keeping track of shapes and data types. It first confirms that NumPy and TensorFlow are installed and reports the TensorFlow version. A flight NumPy array is created, its shape and data type are displayed, and then it is converted into a TensorFlow tensor, again checking shape and type. The script also demonstrates converting the same array into a tensor with an explicitly chosen float64 type, showing that only the data type changes, while the shape stays the same. An integer NumPy array is similarly converted to an integer tensor, and the script verifies that the tensor shapes match the original arrays and that the values are preserved. Overall, it highlights how easily data can move between NumPy and TensorFlow for flexible numerical computing. Core tensor operations. Element-wise tensor operations. Element-wise tensor operations apply the same calculation independently to each position in a tensor, which is essential for numerical work with tensors. When you add or multiply two tensors in TensorFlow, it lines up their entries by position and performs the operation on each pair, producing a new tensor with the same shape. In machine learning, this allows you to refine predictions with element-wise addition or apply masks with element-wise multiplication. Because these operations can be done in parallel, they run very efficiently on GPUs and TPUs and are a core part of tensor computations. Element-wise operations apply a mathematical function to each entry of a tensor independently. These functions can be simple, like absolute value or square root, or more complex, such as trigonometric and neural network activation functions. They are used to transform data, for example by converting signed sensor readings to magnitudes, clipping extreme values, or normalizing image pixels by subtracting a mean and dividing by a standard deviation. In all cases, they change the distribution and scale of the data without altering its spatial or temporal structure. Element-wise tensor operations apply a computation separately to each entry while keeping the overall tensor shape the same. They are essential for combining raw data with model parameters, such as multiplying user and item features in recommendation systems or adding bias terms to adjust predictions. In time series, they let you scale values for seasonal effects or apply nonlinear functions to handle fluctuations. Beyond machine learning, the same idea supports tasks like applying tax rates, converting units, or enforcing constraints in simulations, all by building complex transformations from these simple, local operations. Python code, element-wise tensor operations. This material introduces element-wise operations on tensors using only basic Python and lists. It emphasizes how tensor shapes interact, focusing on broadcasting rules and how shapes can be transformed. The goal is to help you understand how these operations work without relying on external libraries. We begin by creating two one-dimensional tensors, represented as lists of numbers. The first list contains the values 1, 2, and 3 as floating point numbers, and the second list has the same length with the values 10, 20, and 30. Having lists of equal length sets them up for element-wise operations, where each value in one list can be paired with the corresponding value in the other. We then display the first list to show its initial contents before performing any further transformations or calculations. We compare two lists by first displaying the second one, then performing element-wise operations between them. Using a list comprehension, we add corresponding elements from the two lists to create a new list that stores the addition results. We then use a similar list comprehension to multiply each pair of elements, producing another list with the multiplication results. Finally, we print the addition results to show how the two lists combine element by element. We first multiply each element of one list by the corresponding element of another list to show element-wise multiplication. Then we choose a scalar value of 0.5 and use it to scale the first list. This means we create a new list where every element of the original list is multiplied by the scalar. Finally, we output the scaled list to see how each value has been changed by the scalar multiplication. We first apply a nonlinear transformation by squaring each value in the list, so every element is changed independently in a nonlinear way. Then, we clip each value so it must lie between 1.5 and 2.5, which keeps all elements within a chosen range. Finally, we display the results of both the squaring and the clipping to show how these operations modify the original data. This example shows how to manually broadcast a shorter list across a longer one. We first check whether the length of the main list is a multiple of the length of the short list, so we only proceed when their sizes are compatible. If they are not compatible, we do nothing. When they are, we repeat the short list enough times to cover the length of the main list, and then trim it so the lengths match exactly. This tiling process makes the two lists the same length, allowing element-wise operations as if they had started out that way. We manually perform element-wise multiplication between two lists by first extending one list so it repeats until it matches the length of the other. Each element of the original list is then paired with the corresponding element of this extended list, and we multiply each pair. This produces a new list where every entry is the product of the paired elements. We then print the extended list to show how it was repeated, and print the final product list to illustrate the result of this manual broadcasting process. This script shows how basic element-wise operations on lists can be used as simple tensor-like computations. It adds and multiplies two lists element by element, then scales a list by a single number to demonstrate a basic transformation. It next applies a nonlinear transformation by squaring each element, and then clips the values so they stay within chosen lower and upper bounds. Finally, it manually broadcasts a shorter list by repeating its pattern to match a longer list and performs element-wise multiplication, illustrating how broadcasting behavior can be recreated in plain Python without external libraries. Matrix multiplication basics. Matrix multiplication is a key operation for working with tensors because it models how data interacts with learned parameters in machine learning. By combining two matrices into a new one, it integrates information from both inputs. In TensorFlow, this operation is used to transform feature vectors, pass activations through neural network layers, and express relationships between sets of variables. For example, when an image vector goes through a dense layer, it is multiplied by a weight matrix to create a new representation. Understanding how matrix multiplication works with different shapes in TensorFlow is essential for designing effective models. Matrix multiplication combines rows of the first matrix with columns of the second to produce each output entry. And this only works when the number of columns in the first matches the number of rows in the second. In machine learning, you often multiply a data matrix, where rows are examples and columns are features, by a parameter matrix to get outputs. TensorFlow automatically checks that these inner dimensions align at runtime and performs the multiplication efficiently on the available hardware. If the dimensions do not match, it raises an error, so you must carefully design and track the shapes of your tensors. Matrix multiplication becomes especially powerful when extended to higher-rank tensors and batched operations. In many real-world tasks, such as processing time sequences or mini-batches of images, you need to multiply many matrix pairs in parallel. TensorFlow supports this by treating leading dimensions as batch dimensions and applying matrix multiplication across them efficiently. For instance, you can represent user interaction histories as a three-dimensional tensor and multiply each interaction vector by a weight matrix to make predictions. This approach uses TensorFlow's optimized routines, reduces the need for explicit loops, and turns complex workflows into concise tensor operations. Python code, Matrix Multiplication Basics. This script gives a simple demonstration of matrix multiplication using very small tensors, so the dimensions are easy to follow. The goal is to help you focus on how the shapes of the matrices interact and what results they produce. It is not designed for heavy computation, but rather for building clear intuition about the operation. We begin by importing TensorFlow, a powerful library designed for working with tensors, or multidimensional arrays. This step prepares our environment to perform complex mathematical operations efficiently. These tensor operations are crucial for tasks such as matrix multiplication and form the foundation of many deep learning methods. We begin by printing the version of TensorFlow being used. This step is important for reproducibility because it lets anyone running the code confirm they are using the same library version. Different versions can change how the code behaves and the results it produces, so recording the version helps ensure consistent and comparable outcomes. We create a 2x3 matrix using TensorFlow's constant function to represent feature data. The matrix has two rows, where the first row contains the values 1, 2, and 3, and the second row contains 4, 5, and 6. In a machine learning context, each row can be viewed as a separate data point, and each column as a different feature. This simple setup is often used to simulate input data when building and testing models. We create a weight matrix with 3 rows and 2 columns, using a TensorFlow constant so it can transform our feature matrix. Each entry in this matrix is a weight used during matrix multiplication to apply a linear transformation to the input data. The specific numeric values, such as 0.1 and 0.2, are chosen simply to illustrate how changing the weights changes the resulting transformed features. We first print the shape of the features matrix to see its dimensions, which are 2x3. Then we print the shape of the weights matrix, which is 3x2. Checking these shapes confirms that the inner dimensions match, so the matrices can be multiplied. This step helps prevent errors during the matrix multiplication operation. The code first checks whether the number of columns in the feature matrix matches the number of rows in the weight matrix. This alignment is required for valid matrix multiplication. If the dimensions do not match, it raises a value error and stops the operation. This prevents runtime errors and ensures that the matrix multiplication is mathematically correct before it proceeds. We use TensorFlow's matrix multiplication function to multiply two matrices called features and weights. This operation produces a new matrix called outputs. Each value in the outputs matrix is the dot product of one row from the features matrix and one column from the weights matrix. The multiplication is valid because the number of columns in the features matrix matches the number of rows in the weights matrix, so the inner dimensions line up correctly. After performing matrix multiplication, we check and display the shape of the resulting matrix. This confirms that the operation ran correctly and that the dimensions match what we expect. Verifying the number of rows and columns in the output is essential because it ensures the result is valid and can be safely used in later computations. We first convert the features matrix to a numeric array and print it so we can see its actual values. We then do the same for the weights matrix to inspect its numbers. Finally, we convert and print the outputs matrix, which is the result of multiplying the features and weights matrices. Viewing all three in numeric form helps us understand the concrete effect of the matrix multiplication. To demonstrate batched matrix multiplication, we first create a new tensor called batch features by stacking two copies of the original features matrix along a new axis. This stacking operation adds a batch dimension, turning the data into a three-dimensional tensor. With this structure, we can apply the same weight matrix to each element in the batch. This allows us to perform matrix multiplications on multiple inputs at once using a single operation. We print the shape of the new batch tensor to verify that the batch dimension was added correctly. This quick check is important because many later operations depend on having the right data shape. Confirming the shape now helps prevent errors and ensures the tensor is ready for further processing. In this example, we use TensorFlow's matrix multiplication to perform batched operations. We start with a batch of feature tensors, which you can think of as a stack of matrices, and multiply each one by the same weight matrix. This applies the same linear transformation to every element in the batch. The result is a new batch of transformed matrices, allowing us to efficiently process many data samples at once with the same operation. We print the shape of the final batched outputs to verify that the matrix multiplication was applied correctly to every element in the batch. Confirming the shape helps ensure that the operation preserved the expected dimensions. This check is crucial because later steps in a machine learning pipeline depend on having correctly shaped data for further processing or analysis. This script shows how TensorFlow performs basic and batched matrix multiplication. It begins by reporting the TensorFlow version, then defines one matrix of features and another of weights, making sure their inner dimensions are compatible for multiplication. The matrices are multiplied to produce an output matrix, and the script prints their shapes and values so you can see how the data is transformed. It then demonstrates batched matrix multiplication by stacking two copies of the feature matrix into a batch and applying the same weight matrix to each, producing a batch of output matrices. Overall, it illustrates how TensorFlow efficiently handles both single and batched matrix operations. Tensor reduction operations. Tensor reduction operations take a large tensor and shrink it by aggregating values along chosen axes, instead of changing each element individually. They compute summary values such as sums, means, maximums, or minimums, which turn raw data like many sensor readings into concise statistics. These operations answer questions like, what is the total, or what is the average? And they are essential in machine learning for collapsing high-dimensional data into simpler forms. This simplification is used to calculate losses, metrics, and features that guide how models learn. When working with tensor reductions, you must specify which axis or axes to reduce, because each axis represents a dimension such as batch, time, or channels. Reducing over an axis collapses that dimension by aggregating its values while leaving the others unchanged. For instance, reducing over height and width in a batch of images produces the average brightness for each image. Choosing the correct axis is essential, since it determines the shape of the output tensor and the meaning of the results in your data context. Beyond simple sums and averages, tensor reduction operations provide specialized ways to aggregate data that are essential for training and evaluating models. They include finding maximum and minimum values, counting non-zero elements to measure sparsity, and computing norms to help regularize parameters. Reducing loss values to a single scalar supports gradient-based learning, and reductions are often combined with other steps such as normalizing features or aggregating predictions over time. By mastering these techniques, you can better control data flow and condense complex information into useful signals for machine learning models. Python code, tensor reduction operations. This material introduces a simple script that demonstrates how TensorFlow performs tensor reduction operations. It uses small, easy-to-understand tensor shapes, so the results are clear. You are encouraged to run each section of the script and pay attention to the printed explanations. By doing so, you can see how different reduction operations work and how they affect the shape and values of tensors. The script begins by checking whether TensorFlow is installed, and if needed, uses the package manager to install a specific CPU version, TensorFlow 2.20.0. This installation step is essential because the rest of the script depends on TensorFlow. Without it, the script cannot perform the required tensor operations or other TensorFlow-based functions. We begin by importing the TensorFlow library and assigning it a short alias, pronounced TF. This is a standard practice that makes the code more concise and easier to read. Using this alias lets us quickly call TensorFlow functions without repeatedly saying the full library name. It also helps keep the script cleaner and more manageable when we use TensorFlow many times. The code uses TensorFlow settings to turn off GPU usage by making all GPU devices invisible. This helps avoid potential errors related to GPUs. If this attempt fails, for example, because no GPU is present or there is a configuration problem, the code catches the error and continues running normally without stopping the program. We start by printing the TensorFlow version being used. This step is important for reproducibility because it lets anyone running the code confirm they are using the same version. Matching versions helps prevent compatibility problems and unexpected behavior that can occur when different TensorFlow releases are used. We begin by creating a simple, two-dimensional tensor in TensorFlow, filled with specific floating point values arranged in 2 rows and 3 columns. This gives us a small, easy-to-understand data structure that we can use to illustrate different tensor operations. We define it using the TensorFlow constant function so that its values remain fixed during execution, which is ideal for demonstration purposes. We begin by displaying the two-dimensional tensor we created, which contains floating point numbers. To do this, we use TensorFlow's feature that converts the tensor into a NumPy array, so we can view its actual values. Seeing the values in this form lets us clearly check how the numbers are arranged. This verification step ensures the tensor's contents and structure are correct before we apply any reduction operations. In this step, we compute the total sum of all elements in a two-dimensional tensor called values2D. We use TensorFlow's reduce sum function, which adds up every value in the tensor and returns a single number. This single scalar represents the overall total of the data in the tensor. It provides a quick way to understand the combined magnitude of all the values it contains. This code calculates and prints the total sum of all values in a tensor. It uses a TensorFlow operation to compute the sum across every element. The result is then converted to a NumPy value so it can be printed easily. The final output is a single scalar number representing the overall total of the tensor's elements. We are using TensorFlow to perform a reduction on a two-dimensional tensor by summing along the first axis, which represents the columns. This operation produces a new tensor where each value is the total of all elements in one column of the original tensor. In other words, it aggregates the data column by column. This is useful when you want a concise summary of the total for each column. This code calculates and prints the sum of each column in a two-dimensional tensor. It first reports the shape of the resulting column sums, so you know the dimensions of the output. Then it converts these sums to a NumPy array to make the values easier to read. Overall, it verifies that the reduction along axis 0 correctly adds up the elements in each column of the original tensor. This operation computes the sum of each row in a two-dimensional tensor. By setting the axis to work across rows, it adds up all the values in each row separately. The result is a new tensor where each element represents the total of one original row. This provides a compact summary of the data by giving row-wise totals along that dimension. We compute the sum of each row in a two-dimensional tensor to get a one-dimensional tensor of row-wise totals. This new tensor contains one value for each original row. We then display this result along with its shape, which tells us how many rows were in the original tensor. This shows how the data has been aggregated along the row dimension. We use TensorFlow's reduce mean function to compute the average of all values in a two-dimensional tensor. This operation combines every element and produces a single scalar that represents the overall average. The result gives a quick sense of the central tendency or typical level of the data in the tensor. We compute the global mean of the tensor, which is the average value across all its elements. Then we convert this global mean from a tensor into a regular Python number using the NumPy method. This conversion makes the result easier to read and display. This line uses TensorFlow's reduce maximum function to find the largest value in each column of a two-dimensional tensor. By specifying the first axis, it scans down each column rather than across rows. The result is a new tensor that contains only the maximum value from each original column. This line computes and prints the maximum value in each column of a two-dimensional tensor, then shows the shape of the result. It uses TensorFlow's reduce maximum operation along axis 0 so that each column is processed independently. The reported shape confirms that the output has one maximum value for every column, matching the expected number of columns in the original tensor. We create a Boolean tensor by checking which elements in a two-dimensional tensor are not equal to 0, using TensorFlow's not equal operation. This comparison produces another tensor of the same shape, where each position is true if the original value is non-zero, and false if it is 0. This Boolean mask is then used in later steps to count or work with only the non-zero elements in the data. To count the non-zero elements in a tensor, we first create a Boolean mask that marks where the tensor has non-zero values. We then convert this mask from true and false values to ones and zeros using TensorFlow's cast function. Finally, we apply TensorFlow's reduce sum function to add up all the ones in this integer mask, which gives the total number of non-zero elements in the original tensor. This code calculates how many elements in a tensor are non-zero. It starts with a Boolean tensor that marks non-zero positions as true. It then converts these true and false values into integers, where true becomes 1 and false becomes 0. By summing these integers, it obtains the total count of non-zero elements. Finally, it prints this count as an integer, giving a clear summary of how many entries in the tensor are not zero. This script shows how to use TensorFlow to perform reduction operations on a two-dimensional tensor of floating point numbers. It computes the sum of all elements to produce a single scalar, as well as separate sums along each row and each column to reveal how values are distributed. It also calculates the global mean to find the average of all elements and determines the maximum value in each column. Finally, it counts how many elements are non-zero and prints all these results to illustrate how reduction operations can summarize and analyze tensor data. Tensor shapes and broadcasting. Static and dynamic shapes. When working with tensors in TensorFlow, it is important to understand static shapes because they strongly influence how computations are handled. Static shapes are known when the computation graph is built, much like a fixed database schema, so TensorFlow can detect shape mismatches early and plan memory use and operations more efficiently. For example, if your model always processes fixed-size color images, the system knows the input dimensions in advance and can prevent invalid operations, such as combining an image tensor with a scalar. This early knowledge helps catch design errors before long training runs and improves overall performance through better optimization. Dynamic shapes are shapes that are only fully known when the program runs because they depend on the actual data, such as changing batch sizes or sequence lengths in text processing or recommendation systems. In these cases, some dimensions are left symbolic instead of fixed in advance. TensorFlow can still work with such tensors by using partial shape information to infer intermediate results. When real data is provided, it resolves the unknown dimensions, then performs shape checks and broadcasting decisions based on the observed sizes. In TensorFlow, understanding how static and dynamic shapes interact is important for handling broadcasting and shape inference. Broadcasting determines whether tensor dimensions can be combined in operations and whether smaller tensors can expand to match larger ones. When shapes are fully known in advance, TensorFlow can check them at definition time, which makes debugging easier. With dynamic dimensions, some shape checks are delayed until runtime, so errors may only appear with specific data. By knowing which dimensions are fixed and which are flexible, you can write tensor expressions that adapt to varying input sizes while still using static information to keep operations efficient. Python code. Static and dynamic shapes. This script demonstrates how TensorFlow handles static and dynamic tensor shapes. It shows how shapes can be known in advance or determined at runtime, and how this affects tensor operations. The main focus is on broadcasting, where tensors with different shapes are automatically expanded to work together, and on simple shape inference, where TensorFlow deduces output shapes from input shapes. Overall, it provides a basic overview of how tensor shapes behave in common scenarios. The commented line advises installing TensorFlow version 2.20 if it is not already available. This step ensures the script has the required dependency and can run correctly. The comment is meant to help users who might see errors because TensorFlow is missing in their environment. We begin by importing the TensorFlow library and giving it a short alias pronounced TF. This alias makes it quicker and easier to refer to TensorFlow's functions and classes throughout the script. Using a brief name like this is a common practice in programming, especially for long or frequently used library names. It helps keep the code more concise and readable, while still providing full access to the library's features. We first use the operating system module, so we can work with environment variables, and then set the variable named CUDA visible devices to -1. This setting tells TensorFlow to ignore any graphics processing units and run only on the central processing unit. Doing this effectively disables GPU usage and helps avoid errors related to CUDA, which is the GPU-based parallel computing platform and programming interface. We begin by printing the TensorFlow version being used because this helps ensure our work is reproducible. Knowing the exact version lets others confirm they are running the same setup. This is important since different TensorFlow versions can change how the code behaves or how well it performs. We begin by creating a constant tensor in TensorFlow with a fixed shape, specifically a 2x2 matrix of floating point numbers. This matrix contains the values 1, 2, 3, and 4, arranged in 2 rows and 2 columns. Using this simple example lets us focus on how TensorFlow works with static shapes that are fully known when the tensor is created. We are printing the static shape of a tensor, which is the set of dimensions fixed when the tensor is first defined. By checking its shape attribute, we can see these dimensions before any computation happens. This tells us exactly how the tensor is structured at creation time and confirms that its size is known and unchanging during later operations. In this example, we use TensorFlow's shape function to find the dynamic shape of a tensor while the program is running. This function reports the tensor's actual dimensions in memory at that moment, which is helpful when those dimensions can change during execution. By printing the result, we can see how the tensor is currently structured and better understand the data's dynamic layout in the program. We begin by creating a tensor filled with zeros using a TensorFlow function, which lets us initialize data with a specific shape. We then define a batch size of 3, representing how many samples are processed together in one batch. Setting this batch size helps us design tensors whose first dimension can change, so we can handle different batch sizes flexibly during batch processing. In this example, we create a tensor in TensorFlow using a function that fills it with zeros. The tensor has a batch size of 3 for the first dimension and a fixed size of 4 for the second dimension. This means the number of data samples can vary, while each sample always has 4 features. Such a setup is common in machine learning, where the amount of input data can change between runs. This example shows the static shape of a tensor called a flexible tensor. It was created with a TensorFlow function that fills it with zeros, using a shape that specifies a batch size of 3 and 4 columns. The static shape is fixed when the tensor is defined, so it always has 3 rows and 4 columns. Knowing the static shape helps you understand the structure of the tensor before applying any operations to it. We use TensorFlow's shape function to get the dynamic shape of a flexible tensor at runtime. This is important when working with tensors whose size can change, such as those with a variable batch dimension. By printing this dynamic shape, we can observe how the tensor's dimensions are determined during execution. This helps us understand how the tensor adjusts to different input data. A TensorFlow tensor spec defines the expected shape and data type of a tensor. In this case, the first dimension of the shape is set to be flexible, meaning the number of items in a batch can change, while the second dimension is fixed at 4. This lets you handle batches where the number of samples varies, but each sample always has the same size. The data type is set to float32, so all elements are stored as floating point numbers, keeping the structure consistent across different batch sizes. In this example, we are printing the static shape of a tensor specification defined with TensorFlow's tensor spec, which lets us describe a tensor's shape and data type without actually creating the tensor. The printed shape includes a none value in the first dimension, meaning that dimension is flexible and can change. This typically represents a variable batch size, so the number of input examples can vary. Such flexibility is useful when building models that must handle dynamic input sizes during training or inference. We create a new tensor filled with ones that has a shape of 5 by 4, meaning it represents a batch of 5 data samples, each with 4 features. Its data type is set to 32-bit floating point to stay consistent with other tensors in the script. This setup is useful for examining how tensors with different batch sizes interact, especially in operations such as broadcasting. We verify the static shape of the new batch tensor by checking its shape attribute. This confirms that the batch has the expected dimensions and matches the rank defined in the tensor specification. Doing this ensures the tensor structure is correct and compatible with any operations or models that require a specific shape. In this step, we use TensorFlow's shape function to get the dynamic shape of the tensor called the new batch. This means the shape is evaluated while the program is running, so we can see the current dimensions of the batch. These dimensions may differ from the predefined static shape if the batch size changes. This is useful for checking that the tensor size matches what we expect during execution. We define a bias vector in TensorFlow as a constant with 4 elements, each set to 0.5 and stored as a 32-bit floating point type. This bias vector is used to illustrate broadcasting. When it is added to another tensor, TensorFlow automatically expands the bias vector's dimensions, so it matches the shape of the other tensor during the addition. We first check and display the shape of the bias tensor to understand its dimensions before doing any operations. This is important because the bias will later be added to another tensor using broadcasting. In broadcasting, the bias is automatically expanded so its dimensions match the other tensor. Knowing the original shape helps you see how this expansion and the overall operation will work. In this example, we add 2 tensors together using broadcasting. The first tensor has 5 rows and 4 columns, and the second is a one-dimensional tensor with 4 elements, called the bias. Broadcasting automatically expands the bias so it matches the shape of the larger tensor. This lets us add each element of the bias to the corresponding element in every row of the larger tensor, producing a new tensor with the adjusted values. We are looking at the static shape of the result tensor after a broadcasting addition. The static shape is fixed when the tensor is defined and does not change during execution. By inspecting this static shape, we can quickly confirm the tensor's dimensions. This lets us verify that the broadcasting worked as intended, without having to run the computation dynamically. We use TensorFlow's shape function to get the dynamic shape of the result tensor at runtime. This dynamic shape reflects any changes caused by operations such as broadcasting, where tensors with different shapes are combined. By checking the dynamic shape, we can confirm that broadcasting and other operations have been applied correctly and that the tensor's dimensions have been updated as expected. This script shows how TensorFlow works with static and dynamic tensor shapes. It first creates a constant tensor with a fixed shape and compares its static shape, known when the tensor is defined, to its dynamic shape, which is evaluated while the program runs. It then demonstrates a more flexible tensor with a variable batch size, using a tensor spec to represent an unknown batch dimension and allow dynamic shape inference. Finally, it adds a bias vector to a batch tensor to illustrate broadcasting, where TensorFlow automatically adjusts shapes for element-wise operations, emphasizing the distinction between compile-time static shapes and runtime dynamic shapes. Broadcasting rules. In TensorFlow, broadcasting lets you perform operations on tensors with different shapes without actually copying data. It lines up tensor shapes from right to left and checks whether each dimension matches or whether one of them is a single value. When a dimension is 1, TensorFlow conceptually stretches that value across the larger dimension. This makes it easy to write concise operations, such as adding a bias to every element of a vector, or adjusting all rows of a matrix, without manually resizing tensors. When you add a batch of color images to a tensor that holds one correction value per color channel, TensorFlow uses broadcasting to make their shapes compatible. It lines up the dimensions from the end, matching the 3 image channels with the 3 correction values, and treats any missing dimensions in the smaller tensor as ones. This allows the correction values to be automatically repeated across the height, width, and batch dimensions. As a result, a single addition operation applies the channel corrections to every pixel in every image, effectively adjusting the color balance for the entire batch at once. When using broadcasting in TensorFlow, it is important to recognize when it will fail or behave unexpectedly. If, during its right-to-left dimension check, TensorFlow finds dimensions that are neither equal nor equal to 1, it raises a shape mismatch error, such as when trying to combine data for 7 days with data for 5 days. Even when broadcasting is allowed, you must pay attention to which dimensions are being stretched, because mistakes can cause values to be applied along the wrong axes. Building an intuitive sense of how shapes align is essential for using broadcasting correctly in tensor operations. Python code. Broadcasting rules. This script is designed to show how TensorFlow applies its broadcasting rules when working with tensors of different shapes. It uses simple, clear examples, so you can easily see how shapes are matched and expanded during operations. As you run each section, the script prints explanations that describe what is happening and why the results look the way they do. The goal is to build an intuitive understanding of broadcasting behavior in TensorFlow. Before running the script, make sure TensorFlow is installed in your environment. If it is not already available, install TensorFlow version 2.20.0 using the standard Python package manager. This installation step is essential, so the rest of the code can run without errors. We start by importing the operating system module so we can control environment variables, and we set the CUDA visible devices variable to -1 to turn off GPU support for TensorFlow and force it to run on the CPU. This is helpful when testing or when no GPU is available. We then import TensorFlow and give it the shorter name TF, which is a common convention that keeps the code simpler and more consistent across different TensorFlow projects. The code first prints the version of TensorFlow being used so that results can be reproduced reliably. Different TensorFlow versions may behave differently or offer different features, which can affect outcomes. Showing the version lets anyone running the code confirm they are using the same setup. This makes it easier to debug issues and to share and compare results consistently. We begin by creating a base tensor using TensorFlow's constant function to store weekly sales data. This tensor holds 7 values, 1 for each day, representing sales of 10, 12, 9, 11, 13, 8, and 7 units. By organizing the data this way, we can easily apply TensorFlow operations to the entire week at once. This setup also prepares the data for later use of broadcasting, which lets us combine or adjust these sales values efficiently. We check the shape of the tensor that stores week sales data to understand its structure. Printing its shape confirms how the sales values are organized. This information helps us see how the tensor will combine or interact with other tensors in later operations. Knowing the shape is an important step before performing further calculations or transformations. We create a scalar bias in TensorFlow by using the constant function and setting its value to 1.5. This single number will later be added to a larger tensor to demonstrate broadcasting. Through this example, we can observe how TensorFlow automatically handles operations between values that have different shapes. In this example, we add a single scalar value to a vector of weekly sales using TensorFlow's broadcasting. Broadcasting automatically expands the scalar so it matches the length of the sales vector. This allows element-wise addition without manually reshaping the data. The result is a new tensor where every sales value has been increased by the same scalar bias. This example shows how TensorFlow uses broadcasting to add a single scalar value to every element of a tensor. The operation increases each tensor element by the same scalar amount. After performing the addition, the result is converted to a NumPy array, so it is easier to read. The final output displays this updated array with all values increased by the scalar. We use TensorFlow to create a one-dimensional tensor with 7 elements, one for each day of the week. The values are 1, 0, -1, 0, 1, 0, and -1. This tensor represents daily adjustments that will be applied to the sales data for each day. By using this structure, we can modify each day's sales figure individually while keeping the overall data format the same. We combine the per-day adjustment vector with the week sales tensor by adding them together element by element. Because they have the same shape, this addition is direct and does not require any broadcasting. The result is a new tensor, where each value is the sum of the matching entries from the week sales data and the daily adjustments. The code checks the shape of the tensor after adding the per-day adjustment vector to the week sales tensor. The printed shape shows that the result has the same dimensions as the original data. This confirms that the addition was done element-wise. It also verifies that no dimensions were changed during the operation. We represent sales data over 2 weeks by building a matrix from 2 stacked tensors. The first tensor holds the original week of sales, and the second repeats that data with 2 extra units added to each day. Stacking them vertically creates a 2-dimensional tensor, where each row represents 1 week. This structure makes it easy to compare sales between weeks or perform further calculations across multiple weeks. We check the shape of the tensor called 2 weeks, which holds sales data from 2 weeks stacked together. Printing its shape tells us the dimensions of this data. This helps us see how the sales values are organized and confirms that the structure matches what we expect before we perform further operations. We reshape the per-day adjustment vector into a 2-dimensional form with 1 row and 7 columns so it can be broadcast correctly. This allows it to align with the columns of a larger tensor that stores weekly sales data. Once reshaped, we can add the same set of daily adjustments to every row, meaning every week receives the same day-by-day changes. This approach ensures the adjustments are applied consistently across multiple weeks. We use broadcasting to add a row vector to each week of sales data. The per-day adjustment vector is reshaped into a single row and then applied across all rows of the 2 weeks tensor. Broadcasting automatically adds the row vector to each corresponding element in every row, so each day's sales in both weeks is adjusted by the appropriate daily amount. We examine the shape of the tensor called weeks plus day, which is created by adding a per-day adjustment vector after reshaping it to a 2-week sales matrix. This addition uses broadcasting so that the same daily adjustments are applied across each row of the matrix. As a result, both weeks of sales data receive the same per-day adjustments. Printing the shape of this tensor confirms that the broadcasting worked correctly and shows the final dimensions after the operation. We create a column bias tensor to adjust sales data across days. First, we define a constant tensor with the values 2 and -1, which act as biases for 2 different weeks. We then reshape this tensor into 2 rows and 1 column, so it becomes a column vector. This shape allows the bias values to be broadcast over all days in each week, letting us apply these adjustments efficiently to the sales data. We add a column bias to a tensor that holds 2 weeks of sales data by using broadcasting. Broadcasting applies the same bias values to each column across both weeks. The bias is arranged as a column vector, so it can be added to every row of the 2-week tensor. This effectively adjusts the sales data for each week according to the specified bias values. The code prints the shape of a tensor called weeks plus bias, which is created by adding a column bias to the 2 weeks tensor using broadcasting. Broadcasting automatically applies the same column bias across each day in the 2-week period. This operation adjusts the sales data for each week by the specified bias values. Printing the shape confirms the final dimensions of the tensor after this adjustment. We intentionally add a tensor with 5 elements to a week sales tensor that has 7 elements to demonstrate a broadcasting error. Because their shapes do not match, this addition is not allowed and the operation fails. To handle this safely, we place the addition inside a try-except block so that when the error occurs, we catch it instead of crashing the program. We then print the type of the exception to better understand the nature of the broadcasting problem. This script uses simple sales data examples to show how TensorFlow's broadcasting rules work. It first adds a single bias value to a 1-week sales tensor, letting TensorFlow automatically expand the scalar so each element increases by that amount. It then adds a vector of daily adjustments with matching shape, followed by adding the same daily adjustments across a 2-week sales matrix using broadcasting. The script also demonstrates column-wise broadcasting by adding a bias to each week. Finally, it attempts an operation with incompatible shapes, catches the resulting error, and prints it to illustrate how TensorFlow reports shape mismatches. Reshaping tensors safely. Reshaping a tensor means changing how its dimensions are organized without changing the underlying data. You can think of it as rearranging the same set of values into a different layout, such as a column, a grid, or a stack of grids. The crucial rule is that the total number of elements must stay the same before and after reshaping. This conservation of elements makes reshaping safe and predictable, and it ensures that later operations like addition or multiplication behave correctly. When you reshape tensors, you must keep track of what each dimension represents, so the new shape still matches the rest of your computation graph. If the reshaped tensor does not align with the tensors it will be combined with, you can get unintended broadcasting or shape mismatch errors. Reordering dimensions such as days, stores, and product categories in sales data can silently produce wrong results. To avoid these problems, always reshape in a way that preserves the intended meaning of each dimension. When reshaping tensors, you must understand how automatic shape inference and broadcasting interact. Letting the system infer a dimension can be convenient, but it may hide mistakes if the other dimensions are not chosen carefully. This is especially important in tasks like processing batches of medical images, where adding or removing batch and channel dimensions must be done correctly. If you accidentally collapse an important dimension, broadcasting can mix data that should stay separate. Always check what each axis represents before and after reshaping. Confirm that inferred dimensions match your expectations, and test with small examples to catch structural errors early. Python code, reshaping tensors safely. This material introduces the idea of safe tensor reshaping using only Python lists and logical reasoning. It emphasizes understanding how shapes and sizes of data relate to each other, and what changes are allowed without losing or duplicating information. The focus is on recognizing when a reshape is valid based on the total number of elements and how they can be reorganized. Overall, it aims to build intuition for reshaping data structures safely before working with more advanced tensor libraries. We begin with a list called original_data that contains the numbers 1 through 6. This list is a simple, flat collection of values, that we will later reshape into other forms. The specific numbers are not important. They are just an easy example to help demonstrate how reshaping data structures works. We first find how many elements are in the original data by calculating its length. This tells us the total number of items in the list. Knowing this count is essential, because any reshaping of the data must keep the same total number of elements to remain valid. We begin by looking at the original data as a simple list of numbers, so we can clearly see what we are working with. Then we check the length of this list, which tells us how many elements it contains in total. This count is essential because any reshaped version of the data must keep exactly the same number of elements. Knowing the original length ensures that any new shape we choose will be valid and safe. We use a helper function called product to compute the product of a list of dimensions. It starts with a running value of 1 and multiplies this value by each dimension in the list. After processing all dimensions, it returns the final product. This result gives the total number of elements in a multidimensional shape, which is important for reshaping data correctly. We choose a new shape for the data that is compatible with its original size. In this case, the target shape is 2 by 3, meaning 2 rows and 3 columns. This choice is made so the total number of elements stays the same, which allows the data to be safely reshaped. As a result, no values are lost or duplicated during the reshape process. To find how many elements are needed for the safe target shape, we use a product function on the target shape. This function multiplies all the shape's dimensions to get the total number of elements. That total is stored in a value called the safe count, which tells us how many elements are required to reshape the original data into the desired safe shape. We print the target shape we have identified as safe for reshaping, which in this case is 2 by 3, meaning 2 rows and 3 columns. We also show the total number of elements this shape would contain, based on our earlier calculation. By comparing this number with the number of elements in the original data, we confirm that they match. This check ensures that we can reshape the data into the new structure without losing or duplicating any values. To check if a reshape is safe, compare the number of elements in the target shape with the length of the original data. If these sizes are equal, the data can be reshaped without losing or duplicating any values, so you can safely proceed. If they do not match, the reshape is not possible with that shape because the total number of elements would not align. In this example, we deliberately choose a target shape of 4 by 3 that is not compatible with the original data. This means we are trying to form 4 rows with 3 elements each, but the total number of elements does not match what we started with. This mismatch shows that reshaping is not possible without changing the data itself. It highlights the key rule that when reshaping data, the total number of elements must stay the same. To find how many elements are needed for the unsafe shape, we use a product function on a deliberately incompatible target shape. This function multiplies all the dimensions of that shape to get the total number of elements it would contain. The result is stored as the unsafe count, which represents the total elements required for that problematic shape. We print the unsafe shape, which is 4 by 3, along with the total number of elements to check if it matches the length of the original data. This comparison tells us whether the data can be reshaped into this new form. If the element counts match, the reshape is feasible without losing or duplicating values. If they do not match, the reshape would not be valid. The code compares the number of elements in the proposed new shape with the length of the original data. If these counts do not match, it warns that reshaping is not possible because the element totals differ. If unexpectedly the counts do match, it reports that reshaping is safe even though this situation is not really expected to occur. To reshape data into a two-dimensional structure, we first unpack the target shape into two values, the number of rows and the number of columns. These values define the dimensions of the new layout. The rows value specifies how many row elements the structure will have, and the columns value specifies how many elements will be in each row. This step is essential for organizing the data into the desired two-dimensional form. To reshape a one-dimensional list of data into a new row and column structure, we build a nested list where each inner list is a row. We loop over the desired number of rows, and for each row, take a slice of the original list that has as many elements as the number of columns. The start and end positions of each slice are found by multiplying the current row index by the number of columns. This process produces a list of lists that matches the target shape. The code displays the reshaped data structure, which is now a nested list, along with its dimensions. This reshaped form is produced by taking the original one-dimensional list and arranging it into rows and columns that match the previously determined safe target shape. Printing the result allows you to confirm that the reshaping worked correctly and that the new structure has the intended size and layout. This script shows how to safely reshape a list in a way that mimics tensor operations. It begins with a flat list of 6 elements, computes its length, and uses a helper function to check whether a new shape is compatible with that number of elements. A 2x3 shape is confirmed as safe because it matches the original element count, while a 4x3 shape is flagged as unsafe because it does not. The script then manually converts the flat list into a 2x3 nested list and prints the result, emphasizing that reshaping is only valid when the total number of elements stays the same. In this lecture, you learn to create and manipulate TensorFlow tensors with specified shapes and D-types, apply common TensorFlow math and array operations to transform tensors, and explain TensorFlow broadcasting and shape inference in simple expressions. In the next lecture, Lecture B, we will go over AutoGrad with TF.
Thank you for your attention. See you all in the next lecture.